Recording in progress.
Yeah, camps on everyone. Let's start off. So I think this was the last thing that we did. The force between a point charge and a plate. Great, let's go ahead. Let's say we have a field in the region E bar is equal to xi cap plus 2yj cap plus 3zk cap. Find flux in a small cuboid. Of sides dx, dy, and dz. Find charge enclosed in a sphere of radius r. Whose center is at origin. Meaning, if you take a small cuboid, x, y, and z, where this length will be dx, this length will be dz, and this length will be dy. So it's a very small cuboid. So if you're taking a random cuboid somewhere, dx, dy, dz, and if this is the field in the region, the question is how much flux is passing through this small cube. And the second part is if you make a sphere with the origin at a center, then how much charge is enclosed in the sphere? This would be a pretty good one. This is the kind of questions you'll get in advance. Let's get this. Others, do keep your cams on. No idea what you're trying to answer, Jainil. How did you even get that? How do we start this? Think. I'll give you a minute or two. If you got the first part, you'll get the second part. So this could be mostly a more than one choice question. And it's not like this is something completely new. If you remember, the very first question we did was something similar, isn't it? But in this case, we had a whole big cube there. How do we approach? Right, Vihan. Go ahead with the second part. So, see, how do we start? So take this cuboid here. So let this be dx. This is your dz. This is your dy. Now see, just look at the field in the horizontal direction. So here the field will be Ex, the horizontal component of field. Here the field will be Ex plus Dex. So if you travel a small distance, dx, the field will increase by Dex. So if you want to find a flux on only due to this guy, look at this is the area we are talking about. This will be flux due to Ex will be, now you know the area vector will be out of the plane. So out of the box, this will be Ex plus Dex into area, which is dy dz. That is the green shaded area. So this is the area vector, everyone. This is the area vector and this is the area vector. Area vector here is dy dz. Minus this will be Ex into dy dz. So for the Ex ka field, the area is dy and dz. So this will become dex dy dz. Similarly, if you take flux due to Ey, the same way we can argue here. Now this will become dey and the area will become dx dz. Similarly, if you take flux due to Ez, so you're taking flux, due to each component, Ex, Ey, Ez. This will be dEz into dx dy. So if you add all this, you'll get the total flux in the cuboid. Dex dy dz plus dey dx dz plus dez dx dy. This is a general result. This is a general result. Meaning this is independent of whatever function I gave you. This is always the flux in a small cuboid. Now in our question, it is given field E is equal to, so this is the component Ex I cap, Ey j cap plus Ez k cap. So here the field is given as xi cap to yj cap. So I could have given any other field, 3z k cap. So dex will be 1, dex will be dx, dey will be 2 dy, dez will be 2, 3 dz. Is that making sense, everyone? You're just differentiating ex, which is x ka differential dx, 2y ka differential is 2 dy, and dz ka differential 3 times dz. Have a look at this. And this thing in the red is a general solution. Suppose tomorrow if someone gives you field is equal to e power minus x I cap plus e power minus y j cap. So this is your ex. So then dex will be e power minus x into minus. So you substitute that. You're getting it. So we derived this general result independent of e. Here, because the result, the field is good, you get a pretty neat result. So I'll show you the page. So flux on the cuboid will be dx dy dz plus 2 times dx dy dz, 3 times dx dy dz, 6 times dx dy dz. Dx dy dz is nothing but 6 times volume. So dv is the volume of that small cuboid. There. This is the flux in the cuboid. The second part of the question, the flux in a sphere, same logic, integral 6 dv. This will be 6 into volume of the sphere. If you got the first one, second will come automatically, which is nothing but 6 into 4 by 3 pi r cube. Therefore, the flux in the sphere will be 8 pi r cube. And we know, we have proved this last time, the flux is nothing but charge enclosed by epsilon. Therefore, the charge inside the sphere is 8 pi epsilon r cube. This is the answer for the second part. Please have a look at this page first of all. Ask me if there's any doubts on this page. Any doubts on this? You can ask anything that you're not clear. How did I get this Ex? What is this Ey? Anything? And the one in the red box is a general result for any kind of field. Clear this, everyone? Kritik? Nikhil, got this? Surya? Sharman? Arya? This is the second part of it. So once you got the flux in a cuboid, so in any region, the flux is simply 6 times volume. So for a sphere, the volume is 4 by 3 pi r cube. I get the total flux in a sphere. And we know flux is nothing but charge enclosed by epsilon. And we are done. Check it out. Yeah, it's a decent question. Next one. Next one. Clear na, Soham? Parth? Gaussian surface. Now we will come to the Gauss law. Basically, technically, right, we proved Gauss law using Coulomb's law before. So Gaussian surface, it's an imaginary closed surface. So that is the main thing. It should be a closed surface. Again, what is a closed surface? If you take a sphere, it's a closed surface. If you take a cube, it's a closed surface. If you take a disk, it's an open surface. It's not a closed figure. So you should be able to tell there is inside and outside, something of that sort. So an imaginary closed surface about which electric flux is calculated. So this is an imaginary surface. It doesn't exist. It is just your imagination. So we define Gauss law as flux is equal to integral E dot dA. I'll tell you what is that symbol meaning. Is nothing but Q enclosed by epsilon. This is something we proved using Gauss law. So this symbol, right? This is called a closed integral. Meaning it's a regular integration, but the moment I put a circle, it means you are integrating over a closed surface. Means the shape which you have taken must be a closed figure. That is the meaning of the circle there. There. So technically, this is your Gauss law. The flux enclosed by a closed surface. The flux on a closed surface is nothing but charge enclosed by epsilon. So what this means is, if you have a closed surface here, if you have a charge Q1, if you have a charge minus Q2, if you have a charge Q3, and if you have a charge minus Q4, the flux is given by integral E dot dA is equal to the Q enclosed by epsilon. So in this closed surface, the charge enclosed is Q1 minus Q2. Now, can you tell me something? This E is due to whom? This E, electric field, is due to Q1, Q2, Q3, Q4, or is it only due to Q1 and Q2? If the flux is due to the inside charges, the field is due to which charges? This is a field due to all charges. So this is the kind of theoretical notions you'll get. We'll see why. Meaning it looks a little weird, like, if you're saying flux is due to inside charges, why are you taking field due to all charges? And the reason being, do you guys remember last time we proved, if you keep a charge outside, it does not contribute any flux on the system. Yeah, it cancels out. So have a look at this thing. No need to write the notes, you'll get the PDF, so focus on listening and understanding. So the reason is this. So when you calculate the flux integral E bar dot dA, this is E1 dot dA, E2 dot dA, E3 dot dA, and E4 dot dA. So basically, I'm taking flux due to each charge. This is the charge enclosed Q1 minus Q2 by epsilon. This term is 0 and this term is 0. Reason, charges outside do not contribute for any flux. So if someone asks you this question in the exam, right? There was a question like this one time, made it up. In Gauss law, what is E bar? So E bar can be E1 plus E2. It can be just E1 and E2. It can be E1 plus E2 plus E3 also. It can also be E1 plus E2 plus E3 plus E4. All these are valid. Why? You're simply adding zeros, isn't it? If you take only E3, you're simply adding a zero. If you take E4, you're simply adding a zero. It really doesn't matter. What matters is only E1 and E2. The E3 and E4 can be, they're zero. You're getting it? So all these three are right answers. What is that E bar? E bar is E1 plus E2. It can be also be E1 plus E2 plus E3 because E3 DA will be zero anyway. It can be E1 plus E2 plus E3 plus E4 because E4 DA also will be zero. So if you add zeros on the left-hand side, you're really not going to affect the question. So that E bar can be anything, E1 plus E2, E1 plus E2 plus E3 or all. So what is this Gauss law useful for technically? So Gauss law ka primary use, right, is actually to find electric field. Gauss law is useful to find electric field due to symmetrical charge systems. That is important word, symmetrically charged systems. If there is no symmetry, you really can't use Gauss law to find field distributions. Again, what is Gauss law? The total flux on the surface will be equal to charge enclosed by epsilon. That's it. That's a simple definition there. Integral E dot dA is Q enclosed by epsilon. Any doubts on this page? Anything that you're not clear, please ask. I hope everyone got why these two are zero. Because if you take any closed surface and if you put a charge outside, every field line that enters will leave. So it's not contributing any flux. Every line that enters will leave. So outside charges do not contribute for any flux. Flux is simply how many lines are crossing through an area. So let's see how do we use Gauss law to find field. We will take up some known shapes. The first one is an infinite line charge. We have done this in electrostatics. So listen carefully. So we have an infinite line charge. We want to find the field due to this. Anyone remember the results? Field due to an infinite line charge. Anyone remember? Yeah, 2k lambda by r. So do remember that standard stuff. So this is what we do. Step one, assume a symmetrical Gaussian surface. That is important thing. See, what is a Gaussian surface? Any closed surface. But I want to take a symmetrical Gaussian surface. Step two, find flux. Step three, write flux is equal to Q enclosed by epsilon. Great. Can someone tell me what is a symmetrical shape here? Is sphere a symmetrical shape? Again, let me ask you, what do you mean by symmetry? For every point on that shape, right, the line should look symmetrical. So do you think for every point here, can you see the distances are different for the sphere? So sphere is not a symmetrical shape. What about a cube? Do you think is cube a symmetrical shape? From the cube till the center, this is one distance. To the corner, it is another distance. Can you see every point is a different distance from the line? Now, from this argument, you can kind of see a symmetrical shape here will be a cylinder. So for a line charge, a symmetrical shape will be a cylinder. Every point on the cylinder is equidistant from the wire, actual distance. So it should be a closed figure. So we close it on the top, we close it at the bottom. So there, this is your Gaussian surface. This is not real. This is just your imagination. It is just a closed figure. So length L and radius R. Then step 2, calculate flux. We know by symmetry here, the field will be outward, E, 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 and E. So field will be like this, radially away from this. And if you look at the area vector, so here this will be the area vector. For this thing, this will be the area vector, perpendicular, area vector, perpendicular, area vector, area vector. So if perpendicular, there'll be no flux there. So the total flux will be E into the surface area, which is 2 pi r into L. This must be equal to the charge enclosed by epsilon. So this is E into 2 pi r into L, and the charge inside is lambda into L. Lambda is the linear charge density and L is the length of the wire. So E will be lambda by 2 pi epsilon r, multiply and divide by 2, it will become 2k lambda by r. This is how you find, there should be a symmetry here. This is how you find field due to a symmetrical charge distributions. So this is how you find for infinite line charge. But if you guys actually remember how we derived in electrostatics, we did a very big integration and we figured this out. Where are you? There, this guy. You guys remember we took a finite line charge and we got a formula for a finite line. Then we said theta 1 is equal to theta 2 is equal to 90, and then we got this formula. So it saves you a lot of time from all these calculations, but for infinite line charge. Have a look at the derivation. It's pretty useful that way. Now, tell me one thing. Instead of infinite line charge, if I take a finite line charge, matlab length is only till here, is Gauss law still valid? I will take a surface like this. What is the problem? Gauss law is still valid. What is Gauss law? Flux is charge enclosed by epsilon.
सर ऊपर वाली सरफेस पे एरिया और वेक्टर परपेंडिकुलर नहीं होगा.
Yeah, problem ye hoga because it's an unsymmetrical thing. There is no guarantee field will be radial everywhere. Field will be in different directions. So you won't be able to calculate the flux. You're getting it? You won't be parallel to area. That is a problem. You know what is the specialty of an infinite wire? For an infinite wire, every point is a midpoint, isn't it? For an infinite wire, every point is the midpoint. Up and down are equal. You can take a point B here, up and down are equal. It's a midpoint. But for a finite wire, you have field directions different for different things. So Gauss law is valid for finite surface, but you can't use it. Let me show you one more example. Now this we didn't do in electrostatics. We couldn't do actually then. It's quite complex. Infinite charged hollow cylinder. Today's class is quite important. There'll be a lot of theory, and it's all proofs in using theoretical statements. That's what makes it really tough. So focus a lot. Focus. Today's class will be, it's not tough, but it is a little different from what you have done so far. So let's say we have a cylinder. It's an infinitely long hollow cylinder going to infinity. Going to infinity. So this entire cylinder has a charge plus sigma is your surface charge density. So we want to find the field inside and outside. And the radius is r. What are the steps? Step 1, consider a Gaussian surface. So I will take a Gaussian surface. Again, symmetrical will be a cylinder. Distance r. So for r less than r means you're taking inside. The flux will be integral E dot dA is equal to charge enclosed by epsilon. Now, because of symmetry, we can say the field will be radial here. So this flux will be E into the surface area, 2 pi RL. But what is the charge inside of this? It's a hollow cylinder. So is there any charge inside? No, zero. Therefore, field inside is zero. So if you take a hollow cylinder, there is no field inside. For R greater than R, meaning if you take a cylinder, big one, same story. Interestingly, the left-hand side will always look the same. Flux will be integral E dot dA. Q enclosed by epsilon. So this will be E into 2 pi RL. How much charge is inside? All this charge here on this cylinder of radius r, this charge is stuck inside, isn't it? And how much is that? That will be sigma into surface area. Sigma into area will be 2 pi capital R into L. Is that understood, everyone? Whatever charge is there on that cylinder radius r, that is the charge enclosed inside. So we get field is equal to sigma r by 2 pi, 2 pi r will cancel epsilon small r. So E is proportional to 1 by r. So someone asked you to plot the field versus r graph. This kind of looks like hollow shell ka result. It looks like zero inside, then it increases and then decreases. Check it out. This is the field due to a hollow cylinder. We have not done this in electrostatics. So if you try to do this using Coulomb's law, it will be very tough. But Gauss law gives you pretty easily without any integrations and complex calculations. Have a look at how we did this thing. I'll give you one more now. You guys try. I showed you for a hollow cylinder. I'll give you for a solid cylinder. Any doubts on this? Great. Infinitely charged solid cylinder. Remember this thing solid, meaning charges everywhere. Rho is the volume charge density, charge per unit volume. This is radius r. Find the field as function of r. R is the actual distance from the center. Same thing. Find the field inside and find the field outside. Let's get this. I'll give 2-3 minutes. Remember, step 1, choose your Gaussian surface. Step 2, find the flux. Step 3, flux is equal to Q by epsilon. So the left-hand side will actually look same for a hollow cylinder, the flux part. The right side will change. Try. You should definitely know how to, use this flux ka thing. Mains mein you won't have a problem, but advanced mein they do ask questions of this. I'll show you how they'll ask. This is not an advanced question. Rho r by 2 epsilon. Okay. You got an answer? You can type in the chat box to the co-host here. No, there are two logins there. Type to the co-host. Uh, right. Let's see. Most of you got the inside part. Rho r by 2 epsilon. Yeah. So step one, consider a Gaussian surface inside. This is r. The field will be this way. For r less than equal to r, the flux will be integral E dot dl is equal to q enclosed by epsilon. This will be E into 2 pi r l is equal to what the charge inside rho into volume of the cylinder, which is pi r square L by epsilon. So that was an easy one. So that will be rho r by 2 epsilon. And for r greater than r, that means if you take a cylinder outside, then all the charge enclosed will be only up to capital R. The flux will be E into 2 pi RL. So the LHS will always kind of look same. This will be rho. Total volume of that cylinder is pi R square L by epsilon. Are you getting the difference why you're not taking small r on the RHS? Because once you cross capital R, there is no charge. Charge is only till capital R. So this guy would be E is equal to rho R square by 2 epsilon small r. So if you actually try to plot the graph, the function would be a linear function and then it decreases. It kind of looks like solid sphere result. The second case, you take a Gaussian surface like this. There. Do keep your cams on, everyone. Any doubts on this, how we did this? Clear with this thing, Devansh, Daksha? Clear with this? Jainil, Niharika? Next one. Priyansh, clear with this? Now you guys try this. We have a solid sphere whose charge density rho is equal to rho naught r power n for r less than r. R is a distance from the center. and for n not equal to -3. Means look at how the charge is. When r is 0, charge is 0. If you go little outside, charge will be slightly more, then charge will be more, then charge will be more, and charge will be more. You're getting, as you go outside, charge is increasing. So this is a solid sphere where charge is increasing continuously as you go outside. So this entire region here will have small charge. Once you come here, charge is little more. You're getting it? So radially as you go out, charge is increasing. Here, charge is even more. So you have maximum charge on the surface. Something like this. This is how the picture is looking. So as you go outside, the charge is increasing more and more. N is some number. Find the field as function of r. Answer comes in terms of n. So that n can be 0, 1, 1.5, 2.5, anything. But it can't be -3. You will see why. Let's get this. It's not a cylinder, solid sphere. That is wrong. How are you guys finding charge inside God? Inside charge is changing with every small r. You just can't say rho into volume is not the answer. Are you guys taking charge is equal to rho into volume directly? Rho is changing. How are you taking that? Yeah, I have to integrate again. Get it? Rho r power n plus 1 by. Yeah, that looks right, Ishana. Find outside also. Mm-hmm. So how do we consider a Gaussian surface for this? Rho r by n plus 1, n minus 3. So for this sphere, consider a Gaussian surface, which should be another sphere of radius r. We can see by symmetry, it's a radial thing. The field will be radially away like this. And the area vector also will be parallel like this. So E is parallel to A bar. So if you take a point r less than r, inside, the flux will be integral E dot dA. Is charge enclosed by epsilon. So there's a charge enclosed that green sphere, which is E into 4 pi r square so far grade. But how do you find the charge enclosed? Now listen to this thing. We have to integrate here. So I'm drawing this green sphere. So in this green sphere, at a distance x, take a thin shell. So take a thin shell of radius dx. So the charge on the thin shell dq will be density into volume 4 pi x square dx. This is the charge on the thin shell. Because for every thin shell, the charge is changing. You have to add all these charges. So the q will be integral. Rho will be how much? Rho naught r power. So rho naught, I'll take x power n into 4 pi x square dx. This will go from 0 to r. Is that making sense, everyone? How did I find the charge? It's like an onion ka layer, isn't it? It's like an onion, layer upon layer, layer upon layer. So you're finding charge on one shell and then you add up all the charges. So this will be charge density into volume. Rho naught is constant, 4 pi is constant, that is x power n plus 2. So integration will be x power n plus 3 by n plus 3. Limits will go from 0 to 1. This is the reason I gave n is equal to not minus 3. You would have got infinity. You would have got a ln x term, so we don't want to deal with that. So this will be 4 pi rho naught r power n plus 3 by n plus 3. This is the charge inside, everyone. Take this and substitute here. 4 pi rho naught r power n plus 3 by n plus 3. Therefore, the field inside 4 pi will cancel. Rho by r power n plus 1 by n plus 3 epsilon. There, check it out. It's a pretty good result. You should remember this one. This could be even a mains level question. If the charge density rho is equal to rho naught r power n, then the field E is proportional to r power n plus 1. Think about it. When you took a solid sphere, charge density is uniform. N was 0, right? What was the field inside? Kq small r by r cube. So it's r power 1. So inside, if it is rho naught r square, then the field will be r cube. So it will be always 1 power more than the charge inside. So it's a good result. You can remember if it is a integer question or something. Have a look at this, how we integrated. Yeah. Question is still not over. Huh? This is inside. How to find outside? So the same thing, if you want to find the total charge of the sphere, the total charge, the same integration, rho naught, only the limits will change. Limits will go from 0 to capital R. This will be rho naught 4 pi r power n plus 3 by n plus 3. This is the total charge of the sphere. So for r greater than r, that is for the points outside, the flux will be E into 4 pi r square. It actually behaves like a point charge at the center. The total charge enclosed by epsilon. This will be rho naught r power n plus 3, which is a constant, epsilon into r square. There. Outside is easy. You can just find the total charge on the sphere and make it a point charge. So here the limits will change from 0 to capital R. Clear with this, everyone? This is how you integrate. You just can't directly say rho into volume for that green sphere. You have to take an element and then integrate. Clear with this? This is how questions will be framed. This is a good one, decent one. Even though the charge density is changing here, it is still kind of symmetrical. If you see at a given distance, the charge is same. Any doubts on this? This would be an advanced main easy question. It looks scary with n power 3 and all, but if you see, it's really not that much of a solving. Let's see one more. Let's say we have an infinite slab. And if I have to show you the side view, it would kind of look like this. You're getting it's like this. The slab is infinity. Let this distance be d. Let the charge density be rho. So the side view will look like this. This is d. So this whole thing is having a charge. Think of your bread ka slice. If you look at your bread ka slice from the side view, it looks like this. So taking center as origin, x is equal to 0. So this is x. Find the field as function of x. Meaning if you take x less than d by 2, it will be inside. The x greater than d by 2 will be outside. So find the field inside the slab and outside the slab. It's an infinite slab in every direction. Are you getting how the picture is? And if you're looking into my screen, right, this is how it would look. If this, you're looking at the book here. So this is how the thing looks like. So this is the front view. This thing is an entire sheet here. So side view look like this. So here we have, it's like this layer upon layer. So this is the front view you're looking at. So the question is, if this entire thing has a charge density rho, find the field inside the slab and outside the slab. Let's get this. How do we approach for an infinite slab? If you make d is equal to 0, it becomes an infinite sheet. Sheet is nothing but a slab with a negligible thickness. Try. I'll give you a minute. So let me give you an idea there. I'll exaggerate this. So this is the slab here. So this is the center here. So consider a Gaussian surface like this. You can consider a small cylinder inside. So this is x. This is x. And we can see by symmetry, the field will be E this way, area will be A this way, the field will be E this way, and area will be this way. Because there's an infinite sheet, the field will be away from the sheet. So the flux here, so this is for x less than d by 2. The flux will be E into A. The other one will be minus E into minus A. that will be charge enclosed by epsilon. So this will be 2EA. What the charge enclosed? Rho area into 2x, that is the length of the cylinder. Area into length will be the volume by epsilon. Area cancels out. You end up with E is equal to rho x by epsilon. Clear with this? Yeah, right, Falak. It's a linear function. But if you take x greater than d by 2, that means you have chosen a cylinder outside. Same story. The flux will be 2 into EA, but this time the charge will be only up to capital D. So that will be 2EA rho area into thickness of the cylinder by epsilon. You get E is equal to rho D by epsilon by 2 epsilon, which is constant. So outside the thing, there is no field. Is that clear, everyone? You could have used cuboid also, it doesn't matter. So that A is the area of this cross section. And we know rho is nothing but charge by volume, charge by area into D. So if you shift D that side, this will be charge by area, which is nothing but sigma. So this field can be written as E is equal to sigma by 2 epsilon. Do you guys remember that result? Isn't that the infinite sheet ka result? This is also the result of an infinite sheet. Check it out. So inside that slab, the field will increase linearly and then become constant. So if you try to plot a graph, it will increase linearly and then become constant. The direction will change on the other side. So the field will go like this and become like this. This is how the graph will look on either side. You could have taken any shape, doesn't matter here. Cylinder or a cuboid would have worked. That A anyway gets cancelled. Any doubts on how we took an element here? Now, this is what I was saying. These kind of questions you couldn't have solved with electrostatics Coulomb's law. Especially when you have infinite sheets and infinite cylinders, Gauss law is the best way to solve. Have a look at this. Here was thing, Pratik. Ishana, got this? You got it. Maitri, clear with this? Daksha? So let me write down the result here. So if you take an infinite sheet, so if you take an infinite charge sheet, charge density is sigma, the field will be away from the sheet. Sigma by 2 epsilon and sigma by 2 epsilon. If it's a negative charge, then the field will be towards the sheet. If this was minus sigma, then the field length will go towards the sheet. Sigma by 2 epsilon. What if it is an infinite plate? So an infinite charged plate, the difference between a plate and a sheet, you know what? When you take a sheet, when you see from the front or you see from the back, you're looking at the same molecule, isn't it? But when you take a plate, it has two surfaces. Look at your hand, front and back are not same, right? When you look at the front and look at the back, you're looking at different molecules. So basically a plate will have two sheets. So here the field will become double, sigma by epsilon and sigma by epsilon. So it has two sheets. That is the only difference there. There. That's the result for an infinite sheet charged. Or if the sheet is also having thickness, then this is the result. If you make the thickness very small, then yeah, the outside of the field is sigma by epsilon. Sigma is the surface charge density. Any doubts on this? All clear with this? Let's see a question based on this. Let's say we have two sheets, a YZ plane and an XY plane. This is positive, which is sigma. Let's say this is negative, minus 2 sigma. So can you plot? So there are two infinite sheets along XY and YZ plane. Can you draw the field lines and the equipotential surfaces? So for this shapes, infinite sheets, draw electric field lines. How will the field lines look like? These are some pretty good mains level questions. Huh? And draw the equipotentials region. So if I give you two plates like this, draw the field lines and draw the equipotential surfaces. Let's get this. Try. Who said plane lines will originate from the plate perpendicular? Where did you learn that? These are not conductors. These are just charged sheets. Travel making a curve 90. You get a very nice shape, Ray. Let's see. So let's start like this. So due to this, the plus one, the red one, what is the field here? Take any random point here. The field will be away from the sheet because it is positive, sigma by 2 epsilon. Here the field will be away from the sheet, sigma by 2 epsilon. Here the field will be away from the sheet, sigma by 2 epsilon. Here also field is away from the sheet, sigma by 2 epsilon. And what about the negative one? The field will be toward the sheet, which is 2 sigma by 2 epsilon. Toward the sheet, 2 sigma by 2 epsilon. So if you notice something, that means every point in the first quadrant, the resultant will look something like this. And if you take this angle to be theta, we have tan theta is equal to half. So every point in the first quadrant will have field like this. Every point in the second quadrant will have a field this way. This is also theta. Every point in the third quadrant is this way. And every point in the quadrant is this way. And it is constant. If you see, they have a constant magnitude and a constant direction in each quadrant. Now, if you try to draw them, This is plus sigma and this is minus 2 sigma. This is how the field lines will look like. This is how the lines will look like, theta. It's never ending amount of lines, okay? You get a very symmetrical shape. This is how kind of it looks like. Here the field lines are this way. Here the field lines are this way. This is how the field lines will look. That's why there's a good mains question. They will just give you two shapes and ask you the four diagrams, which of the following is the field lines. And how do equipotential surfaces look like? Do you guys remember the properties of equipotential surfaces? The field lines are always perpendicular to the equipotential surfaces. That means if you draw perpendicular to this, so this, the green ones will be equipotential. So if I draw them, equipotential surfaces are perpendicular to field lines. So if you try to draw that, you will see this is how it looks, isn't it? This will not stop. These lines will go on till infinity. This is how equipotential surfaces will look like. Is that making sense, everyone? There's, if I draw the green lines here, you can clearly see here. So for the red lines, draw the perpendiculars, and this is how it looks. Sure? It's a good question. Won't they be out of plane? Yeah, these are planes, right? These are not lines, actually. It's coming out of the plane also. These are 3D, na? I'm just drawing in 2D here. It's a pretty good mains level question. Any doubts on how did I get the shape? Any confusion? Please ask. Next one. Next one. Now this is important. Listen carefully from here. What you're going to do, this will be another type of Gauss thing, mostly statements and all, but you can get pretty good questions on this. So we start with a concept: field inside a conductor is zero. We will prove with this. So if you take a conductor, is placed in an external electric field. So then what happens? If you place it in an external electric field, so let's say we have a conductor here. You took this and you kept it in an external field E bar. Now we know inside there are a lot of free electrons. Tell me one thing: if you put an electron in an electric field, what will happen? Positive charges will go in the direction of the field, negative charges will go opposite to the field, isn't it? So all these electrons will start experiencing force opposite to the field in this direction. So these are called free electrons. Basically, the electrons are free to move inside the lattice. Free electrons move opposite to the field and accumulate on the surface. Then what happens? So you start getting some electrons here on the surface here. So electron, 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 electron. At that time, we'll get some positive charge also on this side. There is still an electric field here. So now if you look at an electron here, this is experiencing two forces. It experiences a force due to this external field, E into E. It also experiences a force due to the induced charges. So this is an intermediate stage. So these charges which have accumulated, there is an F induced force. Think of like this. So when you have this, when you already have a negative charge here, if an electron tries to come here, what will happen? These electrons which are already sitting here, they will repel this electron, right? They'll say like, yeah, don't come out from here. Similarly, all the positive charges here will attract this electron. So the induced charges inside the conductor will start generating a force opposite to the external field. So you'll start getting kind of an opposition inside. Right? Due to induced charges which opposes the external force. So basically the induced charges are fighting with that external force. But initially the external field is still stronger. F external is greater than F induced. So electrons will continue to go forward. So this accumulation will keep happening until at some point you have accumulated so much charge. This whole surface becomes induced with a very good amount of charge, minus Q. This side becomes some plus Q. Now, if you look at the electron in the middle, it will experience the two forces, the F external and the induced forces are so strong they cancel out the charges inside. So in steady state, F external becomes equal to F induced. Therefore, net force is zero. If force is zero, field is zero. Therefore, net field is zero. There, this is the proof that if you take a conductor and put it in a field, an external field, the field inside will be zero. If you see there are no numericals, no derivation, no formula, it's all just statements only. Again, let me explain it in brief. What this thing says is, if you have a conductor, if you put an external field, this external field will start attracting the electrons this side. So when the first electron comes here, there is no problem. But when the second one tries to come, these electrons will repel this. When the third electron comes, and so on, as the electrons are coming more and more and more here, these electrons which are trying to come will get repelled. And you get positive charges here because it's a vacancy. This will get attracted. So the minus and the plus will create a new force F induced inside. And this outside field is attracting you. As long as the external field is stronger, more and more electrons will accumulate. At some point, the induced charges will be so high, they will cancel out the external field. Is the story making sense? So this is how you always argue. Why is the field inside a conductor is zero? You start like this. If the field is not zero, that means there will be a force on electrons. These electrons will accumulate on the surface. They'll induce charges, right? And this will keep on happening till they cancel the external field. Therefore, the total field has to be zero inside. Is that making sense? So if I ask you this question, is this electron experiencing force due to the external field? Yes. Is it experiencing force due to the induced charges? Yes. What is the total force? Zero. Is that making sense? Just have a look at this thing. Quite an important statement here that the field inside a conductor is zero. Any doubts on this page? Great. So let me make a statement here. So the field due to induced charges cancels out the external field. So this will be the final statement. The field due to field inside a conductor. So if you take a conductor and put it in a charge distribution, no matter how much charge you keep outside, the field inside a conductor is always zero. Due to static charge distributions. It's always zero. Tell me one thing. You wanted the force by field and by charges inside differently, right? I don't know what you're asking. Taksha, what do you mean by that?
So like the electric field is actually responsible for the induced charge inside, right? So why?
That induced charges will create one more field, na? Opposing. Because you're inducing charges, they're also charges only, right? It's like this. If I start fighting with you, you'll fight back, right? You won't just sit there and take the beating, something like that. So if this external field is pulling the electrons, these induced charges will start creating their own field. They'll counter the external field.
Okay. Well,
Now, this thing, if suppose you take an insulator, what happens? What is the difference between an insulator and a conductor? In insulator, you don't have electrons, isn't it? You don't have enough free electrons. All are stuck inside the nucleus. So inside an insulator, there's no guarantee field is inside zero. So in an insulator, since you don't have enough free electrons, you won't get enough induced charges. So field inside need not be zero, meaning you can create a special case to get zero, but there's not necessary. Field inside need not be zero. Therefore, since it doesn't have free electrons, and one more thing, if you take a conductor, now just now we proved in a conductor the field is zero. If field is zero, what happens to potential? Field is minus dV by dr. If field is zero, this implies potential is constant. That means if you take a conductor, the potential inside is constant. It's an equipotential region. That means, did you ever see birds there? Or remember I told you this thing once before. So I think somewhere in 2016 or something in Vikhroli, right, when the local trains were going, one day accidentally this 10,000 volts ka wire, it got cut and it fell on the train. Remember this I told you? So imagine you're sitting inside a train and the 10,000 volt ka cable wire, the wire fell on the train. Normally in real life, what happens, right? There are safety systems. Immediately the power supply gets cut off, all the trains stop. But let's say, unfortunately, that day didn't happen. And you're sitting in the train. What should you do? Option one, start jumping, shouting, and crying and pushing people. Decent option. Option two, just shut your mouth and sit there. Option three, aram se get down from the compartment. Option four, jump from the compartment. What do you think we should do? should start shouting, panicking, and throw people outside. Now, in this, what is the worst option? The worst option is aram se getting down is the worst option. The thing is, as long as you sit inside, now what will happen? Say, let's say you touch here. Now, I agree, this is 10,000 volts, but you're touching this is also 10,000 volts. So, what is the potential difference? Zero. So, what kills you is not the potential, it kills you. What kills you is potential difference. Are you getting it? Potential is not dangerous, potential difference is dangerous. So as long as you're inside the compartment, you're safe, because the whole thing is a conductor. The potential will be 10,000 volts. The problem comes when you try to get down. When you're trying to get down, the moment you put your leg down on the ground will have zero potential. This will have 10,000 potential. You will get a shock of your lifetime. First of all, you'll get fried. Ever seen a bird getting fried on electric wires? I thought so. I mean, normally the same reason, why birds don't die. So if a bird is sitting on this, something like this, that's a bird. So if you see here and here, the potential is same. That's the reason the bird doesn't die. But let's say there is one more bird here. And if these two birds, by chance, let's say the wings touch each other, and then you'll get a shock. Both the birds will die. I think when I was in school, I saw a bat dying like that. There was a bat which got stuck between both of them and it got fried. So most people think, you die because of electric shock, but actually, when you get a shock, right, the current that flows through your skin generates so much heat. Most people die because of third-degree burns. So almost 85% of the issues are with the electric burns. Actually, it is not the shock. So the best thing is to just shut up and sit inside, right? Let people come and take you out. The second best thing is, if at all you have to get down, jump in such a way when you are touching the ground, make sure you're not touching the container or that whatever is the railway car box. Getting it? Touching the box and the ground is the worst thing for disaster. So same logic basically. So you are actually kind of safe inside that. So it's an equipotential region. So how they'll ask a question. So if it's an equipotential region, the field lines will always enter and leave perpendicularly. Therefore, if you put a conductor in a field, the field lines will always enter and leave a conductor perpendicularly. Leave a conductor perpendicular to the surface. So there is a question like this in one of the PYQs. There is a conductor here. And let's say it has a cavity also. And the question was like this. So there's a plus Q charge here. How will the field lines be? How do you think the field lines will be? Can the field lines go like this? Why? The field lines inside the conductor are zero. So the field lines will go like this. They will enter the surface perpendicularly. They will leave the conductor perpendicularly. And since there are no field lines inside the conductor, you will find there are no lines inside. None of the lines will enter the cavity. Because the conductor will block any line from entering inside, so you'll not get any field lines. This is what we call a shielding effect or screening effect. In chemistry, you must have studied. If you have a nucleus and if you have an electron vacancy in the first orbit, if an electron jumps from higher orbit to this first orbit, so this electron will create a repulsion. So it's called a screening constant or a screening effect. So this incoming electron will think there are Z minus 1 protons inside. Do you guys study that in chemistry? Shielding effect, screening effect. So basically, as long as you're inside the cavity, you don't know what is happening outside. So there are more field lines here. This is how the field lines will look. They'll enter the conductor perpendicularly. They will leave the conductor perpendicularly. So this will be some minus charge here. This will be some plus Q charge here. Total will be zero because it's a neutral conductor. Now we can answer something here. So there's one more theoretical question you can ask. So on this conductor, you're saying there's a minus charge, and you're saying there's a plus charge. So is it possible to have a field line coming from here and here? Because we studied field lines will go from positive to negative, isn't it? Is this possible? Why? What is the problem? Why can't you have a field line like this? Why can't you have a line going from positive plus q to minus q? We did discuss this. These kind of field lines are not possible. Simple reason. Do you guys remember the statement? In the direction of the field, the potential will decrease. So if you have a field line, means if you go from here to here, you're saying indirectly this point and this point have different potential. But we know conductor is equipotential. Therefore, you cannot have a field line like this. This we did in the relation between field and potential. In the direction of a field line, potential will change. But the conductor is equipotential. So, so point A and point B will have the same potential. This will be a good statement question. Why can't you have a line like this? So theoretical questions, right? This is how you will get them. There. So this is quite an important concept. The field inside a conductor is zero. And what is the proof? If the field inside is not zero, the electrons will keep going, creating more and more induced charges till these induced charges will cancel the external field. Therefore, the field has to be zero. Since the field is zero inside, it has to have an equipotential surface. Therefore, all the lines will enter and leave perpendicularly. Is this clear, everyone? Any doubt so far? Take a break. Come back with 7.5. We'll continue from here. Any doubt so far?
So,
Daksha.
so in case of the train thing, so if I have
Plane.
one,
Uh,
so if I have one hand on one side and I'm still in the uh, box or whatever, one hand is touching somewhere, the other one is also touching somewhere. And if my legs are on the ground, then like the
you're
circuit will
gone.
complete, right?
No, you're gone. No. And it doesn't matter if you're touching here and if you're touching here and touching the ground. This is 10,000, this is 10,000, this is zero. Current will come from both the sides. Both the hands will get fried. At least before it was better. One hand used to get fried and one leg used to get fried. Now both the hands will get fried.
Okay,
You are more evil actually. So you will kill the person more badly. So yeah.
okay.
Chalo, take a break. Come back in 10 minutes. Let's go ahead. So we proved one important thing, that if you take a conductor and no matter what you do, put a charge outside, put a field, anything, the conductor inside the field is zero. Others, do keep your cams on or else you'll be removed from the classroom. Now, this gives us something. How does charge distribute on a conductor then? So one thing, field is zero. So charge distribution on a conductor. So let's see a few cases. Case one. You took a charge Q and you gave it to a conductor. Meaning you took a conductor and you gave a charge Q. So now the doubt is, where will this charge be? Can you have charge inside like this? So we will prove this, with Gauss law, but there is an easy way to figure it out. Tell me one thing. If you take a positive charge and keep all at one place, what do like charges do? They repel each other. So you tell me then what's the thing that will happen? So they will push each other in such a way, they will try to go as far as possible. Imagine, you and another person, right? You both hate each other. And if you put both of you in a room, where will you sit? I'm pretty sure you won't sit together, isn't it? You will try to sit as far as possible. And what is as far as possible? The surface. So here, if you put a bunch of positive charges, they will repel each other and they will repel till they reach the outermost edge of the surface. So that is a proof that there will be no charge inside. But anyway, let's prove it. So if you take a conductor, so if you consider a Gaussian surface, so consider a Gaussian surface anywhere. Now, just now we proved the field inside a conductor is zero. E is zero since it's a conductor. If field is zero, then this implies, therefore, flux is zero. If flux is zero, that means the Q enclosed is zero, meaning you cannot have any charge within the red color boundary. Therefore, you cannot have any charge inside the conductor. Charge cannot exist in the bulk of a conductor. Bulk meaning in that solid. You can't put a charge inside a conductor, a solid, and it won't there, it'll just come out. So this is what will happen. So whatever charge Q you gave, everything will come to the surface. Charge will not enter inside. Is this clear, everyone? Others, can you keep your cams on? Arnav, Keshav, Soham, cams on, everyone. So if you put a charge Q on a conductor, it just comes to the surface. Any doubts on this? Great. Second one. Now it is on. Previously it was not. Okay. Case two, what if you have a conductor with a cavity? So if you take a conductor and if you put a cavity, so the doubt is, by any chance, the charge will go inside. Again, you can logically prove this. Think about it. By chance, if any charge comes here, what will happen to the positive charges? They'll repel each other. If they repel each other, won't they go to the farthest points between them? That will be the outermost surface, isn't it? So technically speaking, you can't have charge inside. But anyway, let's prove it. So we have a conductor with a cavity. Since we don't know how the charges are distributed, let some charge go inside. Let's assume small q. Then the remaining charge will be outside, q minus q, because the total charge has to be conserved. Same story, consider a Gaussian surface. So we will consider a Gaussian surface enclosing this cavity. Field is zero, implies flux is zero, implies the charge q must be zero. That means if you put a charge q from outside, the charge will not enter the cavity. The final picture will look like this. So if you take a conductor and if you give a charge q, all the charge will come to the surface. There will be no charge inside the cavity. Play with this. So if you give a charge to a conductor from outside, there is no way it will go inside. Clear? Then how do we get charge inside of the cavity? So I have divided this all into cases. So as long as you know the cases, things will fall in place. So if you take a conductor and if you take any random cavity inside, and let's say you kept a charge q inside. This is a neutral conductor with a cavity. The charge plus q is placed inside cavity without touching the surface. Because the moment you touch the wall, the charge will just flow outside again. So you don't want to touch the walls. Now what happens? This is a good one. So listen carefully. So when you made this cavity here, since this is a positive charge, this will attract all the electrons in the surrounding, and all these electrons will start coming towards this surface. Let the charge be minus q. We don't know how much is that. Because the whole thing is neutral, we'll get a plus q charge on the outside. Plus q. Think of like this, huh? Imagine you go to a stadium for maybe a music concert or show or something, and let's say they have a stage in the middle. Now tell me, if the singer is singing here, what will happen to the crowd? Do you think crowd will sit very far away from him? Won't the crowd start flocking around him? If the crowd is flocking here, then the seats on the corners will become vacant, right? Because everyone wants to get to the center. So it kind of looks like that. The plus q charge will attract all the electrons towards it. So all the electrons will accumulate on the surface. And these electrons are coming from the surface, so that will become a positive charge. So positive charge is nothing but absence of electron. But are you getting this? Now we want to find how much is that minus q. Again, same story. Consider a Gaussian surface. Remember, I have taken a random surface, a random thing. So when a Gaussian surface E is zero, it's a conductor. Therefore, flux is zero. Therefore, charge enclosed must be zero. And q enclosed is q minus q. Therefore, q is equal to capital Q. That means if you put a charge q inside a cavity, you will always induce equal and opposite charge. So this is how the final thing will look like. So if you put a plus q here, you will induce a minus q charge on the surface of the cavity, and you will get a plus q charge on the surface. This is how the distribution will look, everyone. Is that clear, everyone? So if you put a charge inside the cavity, on the surface of the cavity, you'll get a minus q, and outside you'll get a plus q. Because the whole thing is neutral, charge on the conductor has to be conserved. These are the three main cases. If you know these three cases, I think you'll be able to understand. Now, if you combine, mix, and match, right, you will get different cases. Any doubts on this? Clear? Let me take an example. So let's say we have a sphere, and let's say we have one more sphere cavity here. And let's say you kept a charge q here, not in the center, somewhere here. Can you tell me how will the field lines look like? Can you draw the field lines for this system? Try, I'll give you a minute. You kept a charge q not in the center, somewhere here. How will the field lines look for this whole system? Inside, outside, everywhere. Try to draw roughly for a minute, then I'll show you. You can verify whether you got the same thing. Show you? See, if you keep it here plus, because this surface is closer, you'll get more negative here. You'll get less negative here. So you'll get a non-uniform distribution. And the field lines will look like this. So you'll have a bunch of field lines here. And you'll have less field lines here. And this total charge will still be minus q only. And outside, you'll get a plus q, which will be again uniform. So whatever happens inside, the outside guy doesn't know. So if I actually draw these field lines, this is how they will look. And outside the field lines will be radial. Yeah, it's a conductor. That is the whole story. It is always a conductor. So here, this is what will happen. The charge inside let me just draw these lines again. They got too cumbersome. They look like this. So the charge inside the spherical cavity is not at the center. So therefore, it induces non-uniform charge. So if you had kept at the center of the cavity, you would have got a uniform inside also. It induces non-uniform charge whose value is still value is minus q only. Non-uniform charge, but the total charge is still minus q of minus q. Like I said, you'll always induce equal and opposite charge, but it's not uniform field. So because of this, inside the cavity, you'll have a non-uniform field. And once you go outside, the outside charge is uniformly distributed because the inside charges don't interfere with this. So field lines from inside the cavity do not come out because there's a conductor in the middle which will not let any field lines come out. Therefore, charges outside. We will talk about this thing. It's an important one. So charges outside are not affected by the plus Q and its induced charges. Have a look at this. So let's discuss this in more detail. So that means no matter what you do inside, meaning there's a question like this in one of the mains Kathinga. If this plus Q which is inside is moving inside like this, the question is what happens to the outside charge? Nothing happens. That guy doesn't even know that something is inside. Think of like this. If I put you in a room which is soundproof and inside you're shouting, do I even know what you're doing outside? Now, if you go back to the definition of field lines, do you guys remember the field lines definition? Look at the statement. A body modifies its surrounding by creating field lines. When another body enters this region, means when another charge enters this field lines, you interact. So that means two charges interact with each other because of field lines. But in our thing here, the field lines from inside are not even coming out, isn't it? So the outside charges don't even know that someone exists inside. It's like that only. Like if I keep you in a room which is soundproof, and no matter how much you shout, no one is going to hear your voice. So no one knows that you're there inside. Make sense? So let me show you an example. So if you take a random conductor with a random cavity, let's say we have a charge here Q1 and we have a charge here Q2, and let the distance between them be d. Now see what happens. This Q1 will create an induced charge here. Again, we're only talking about this charges inside. This is minus Q1. So all the field lines from here, they will just end on the surface. Not a single field line from inside will come outside. Getting it? So if none of the field lines are coming out, then what will Q2 think? Q2 doesn't know that there is someone inside. Q2 does not know there is a cavity only. This Q1 will come outside. We are ignoring that. We are just looking at the inside part. Ignore surface charge for now. So that means, can I say, make a statement like this? So the force on Q2 due to Q1 and the induced charge minus Q1 is 0. So I can write force between Q1, Q2 plus force between minus Q1, Q2 is equal to 0. Therefore, force between minus Q1 and Q2 will be minus, using Coulomb's law, K Q1 Q2 by d square. Does Coulomb's law care about the medium between them? The force between two charges is independent of the medium between them. So that means, you know what you have proved indirectly? So all this random surface which you have taken minus charge. Now I don't know how is this charge also, but we can confidently say the force of attraction between them is equal to k q1 q2 by d square. Is that making sense? This is the force between the minus q1, the induced charge, and this thing. Any doubts on this? So if I ask you this question, say, is q1 and q2 repelling each other? Yes. Is minus q1 and q2 attracting each other? Yes. But if I take q1 and this thing together, q2 doesn't know anyone is inside. Net force is 0. Is that making sense, everyone? Any doubts on this example? Please ask me. So the charges are induced on the surface in such a way the field lengths won't go out. So q2 doesn't know there is a force inside. So this point charge ka force must be equal to this surface ka force. Clear with this? Any doubts on this? Darya? Clear with this? Arush? Palak? Surya? Krish? Next one. Let me take one more example. See, this is what I said. Did you observe something? Did I use a single equations, any formula, nothing, right? Everything I'm just making statements because it is like this, we have to do this, because this, it is that. That's what makes these questions different. Let me take one more example. Suppose if you have a conductor, we have a cavity. Let's do the other way around. Let's say we have a charge Q1 here, and let's say we have a charge Q2 here. So what will this Q2 do? This Q2 will induce charges on the surface. Now we are doing the other way around. So this will induce some minus Q charge. And this will induce some plus Q charge. Now, did you observe one thing? Not a single field line from outside will enter the cavity. Vice versa, right? If I put you in a room which is soundproof, if no matter how much I shout inside, you can't hear also. You also can't hear, right? If I can't hear you, you also can't hear me. So here the plus Q2 and its induced charges. So this is the important thing. So charges inside the cavity will not interact with outside charges. Outside charges will not interact with the inside charges. And its induced charges, which are minus Q and plus Q on the surface, do not interact with charges inside the cavity. Therefore, the force between Q1, Q2 plus force between minus Q, Q and Q2, this resultant must be 0. This is what we call a shielding effect or screening effect. So basically the charges on the surface will induce in such a way they won't let any field lines go inside. So if you put any charge inside, it will be isolated. And this is something, right, you must have noticed it on daily basis. Ever observe this thing? When you go into a lift, your signal goes off. You're talking on a phone, you enter a lift. What is a lift? A lift is made of metal, isn't it? It's a metal box. So the moment you enter into a lift and the lift closes the doors, you have created a conducting box and you're inside the cavity. And what is signals? Phone signal is nothing but electromagnetic signals. So all the signals will come and stop on the surface. So you won't get any signal inside. That's why your phone doesn't work or your signal goes very bad. Notice that anytime? That way. So that means if you're going in a car and let's say a lightning bolt comes and hits the car, what do you think will happen? And if you're sitting inside, you are actually kind of safe, isn't it? All the charge that comes outside will flow here and will go through the tires into the ground. None of the charge will enter inside the car. You're actually safe inside that. The only problem is this: when the thunderbolt passes through the car, there is a chance the car will get overheated. Then the whole thing can get really heated up. The heat might kill you, but the current won't touch you. Is this clear, everyone? There, we started all this theory with one concept that the field inside a conductor is zero. And from there, we started with this thing. If you put a charge Q in a conductor, what happens? If you have a cavity, what happens? If you put a charge inside a cavity, what happens? You guys should definitely revise all this stuff after today's class, maybe tomorrow maximum. Take out the notes, read each line by line, and try to do all these questions. So if you put a charge inside, it doesn't know there is something outside. If you put a charge outside, it doesn't know there is something inside. Clear with the stuff? Let's see a question. Let's see how the last questions on this. Let's say we have a spherical shell, we have a cavity. So this is your center. Here we have a charge Q1, which is not the center of the cavity. And here outside we have Q2. So distance between Q and Q2 is D. Distance between the center and Q2 is Z. R is the radius. So now we are putting inside outside everything, right? So this is a sphere with a cavity. First thing, can you draw the charge distribution roughly? How will the charges look like? Draw the charge distributions. Next thing, find force between Q2 and induced charges on inner surface of the cavity. Find force between Q2 and the conductor. Find potential at the center. And let's say you have taken a point A here. A is a point on the surface and point A. Let's get them all. Let's start from the first one. Draw the charge distribution. Then we will take it one at a time. This is how questions will be framed in Gauss law. Let's see the charge distribution. So listen here. So this Q1, what it will do, it will induce charges. So it will be non-uniform here. It will be plus here, minus there. It will be minus. And that value will be minus Q1. And this will be non-uniform. So this charge will be minus Q1. You'll induce equivalent opposite charges, and this will be non-uniform on the inside surface. And this charge will come onto the surface. You will get a uniform outside. So this will be plus Q1, which is uniform. This is clear. But other than this, now there is one more guy here. This Q2 will not keep quiet, isn't it? This Q2 will induce one non-uniform charge on this surface, which is minus Q, and it will induce a plus Q on this side. So basically on a surface, you have a uniform and a non-uniform. So the whole thing actually gets messed up. You'll get a non-uniform on the surface. Is this making sense, everyone? So on the surface, there are two charges. One is Q1, which is uniform, and minus Q1 plus Q, which is non-uniform. This is coming because of Q2. So the overall surface will look kind of messed up. Now the force between Q1 and Q2 plus the force between minus Q1 and Q2 must be 0. This is the charges inside the cavity. So this Q1 and this minus Q1 together will not interact with anyone outside. That was your second question, isn't it? Find the force between the induced charge on the cavity, that is this guy, and that one. The distance is d. So this is k, Q1, Q2 by d square is force between Q1 and Q2. There. So this is the attractive force, k, Q1, Q2 by d square. Is this clear, everyone? So this is the force between this minus Q1 charge here and this charge Q2 here. Directly you can't find, you always have to do it indirectly. So this is how you argue. This Q1 and this minus Q1 will not interact with Q2. Therefore, force between Q1 and Q2 must be equal to force between minus Q1 and Q2. Is this clear? Now, can you do the third part? Look at the third question. Find the force between the conductor and Q2. Now, when I say conductor, what are the charges? This charge, isn't it? The whole charges you have to take. You have to find all the charges on the conductor will interact with Q2. How much is that force? Try. I'll give you a minute or two. How do you find the force between the conductor and Q2? Maybe, that's not the answer. Nee, Poroja, that's not the answer. Nee, Falak.
So could you just show the question for a minute?
That was the question, na? Find the force between the conductor and Q2.
Okay, sir.
How do we do that? Before the conductor wasn't charged, due to Q2 it got charged. So why isn't the distribution outside Q2 minus Q1? So if this is Q2 minus Q1, what are you talking, right? How did you get Q2 minus Q1? See, if you put a charge outside, I don't know these values. You can never find these values. Are you getting, Surya? Only when you're inside, see, we proved only one thing. If the charge is inside, it will create equal and opposite charge. If the charge is outside, I don't know what are the induced charges. Are you clear? You can never find the Q1 minus Q. Now look at the third part. What was the question? Find the force on a conductor. So when you say conductor, what are there? So on a conductor, we have three things. We have a uniform distribution. Q1. We have a non-uniform distribution. We have a non-uniform distribution. Minus Q and plus Q. And we also have this distribution minus Q1. Isn't this the meaning of a conductor? Outside there are two charges, inside there is one charge. And where is your Q2? Q2 is here, Q2 is here, and Q2 is here. So what's the force between these two? The force between these two, F1, will be K, Q1, Q2 by Z square. What is the force between these two? This force cannot be found. I don't know the value of these charges. I don't know how they're distributed also. This cannot be calculated. So the third answer is we don't know. We can't calculate. The problem is this Q2 will create an induced charge on the surface. That charges will mess up the whole thing. I don't know the value of small q and I don't know how they're distributed. I can't calculate this force. This to be just calculated. This is K Q1 Q2 by D square. This came from the second part. So for the second part, third part, there's no answer. Is this clear, everyone? You cannot calculate because of this one. It messes up the whole thing. So people who got the answer, you're wrong. You can't find the answer. Clear with this? Devansh, Daria, clear with this? Vihan.
So for the last part, wouldn't F3 should be 0 because of minus Q1
This
and
one I
the
got.
charging side?
Is Q1 part of a conductor?
Okay, so that excludes Q1.
Yeah. Clear with this? Question still not over. There's a fourth part. Can you find the potential at the center and point A now? I hope everyone is getting why these questions are a little different. These are not like any problems that we have done before. It's all statements only. Can you find the potential at the center and point A? A is a point on the circumference. Try. I'll give you a minute. Find the potential at the center due to this distribution. Again, remember, when I say potential, you have to find due to this guy, this guy, this guy, this guy, this guy, and this guy. You have to find due to all of them. Try. Take a minute or two. If you see, the story is the same. So we have this, we have this, we have this, and we have a charge also outside. So we have a Q1, which is uniform here. You want to find at the center. So due to a shell, what is the potential at the center? K Q1 by R. Agreed? Now, you will have non-uniform charges here, but luckily, all the charges are equidistant. If all the charges are equidistant, potential is a scalar quantity and the total charge is zero, this potential will be zero. You cannot find the force due to these guys, but you can find the potential. Since all charges are equidistant, it will be kq by r and total charge is zero. Even though it is non-uniform, you can still find the potential. And V will be k q minus q by r, which is zero. This will be interesting. So this guy will be a non-uniform minus q1, and this guy is plus q1. The center is somewhere here. And just now we said these two guys will not interact with anyone outside, isn't it? So this, the potential V3 will be zero. So basically this is due to q1 and minus q1. And you want to prove it, there's a way to prove this. What is the field outside due to these things? Can I say like this? V center minus V infinity will be minus integral E dot dr. But this is zero. That is the field is zero. Just give me a minute. Yeah. So the field outside is zero. Field outside due to the cavity will be zero. Therefore, this is zero. Therefore, V center must be equal to V infinity. What is the potential at infinity? Zero. There, this is how you can prove it actually. That these two charges will not create any potential outside. They are just gone. Matlab, these two things will not exist for anyone outside, isn't it? Anyone outside will think they don't exist only. So what is the potential then? And then we have one more charge, Q1, Q2, and this is the center. This distance is Z. So this will be the fourth potential V4, which is KQ2 by Z. There. So the potential at the center will be due to the shell KQ1 by R. This is 0, 0, and that is KQ2 by Z. Is this clear, everyone? Isn't that the meaning of potential? When I say find the potential, you have to find the potential due to every possible charge. Have a look at this. Then what about the potential at A? V center will be equal to VA since it is a conductor. Conductor is equipotential. So you need not calculate for A separately. Every point on the conductor will have same potential. So if you can find on the center, I can find anywhere. There. This is how they'll frame questions in advance. You can actually make it even more dangerous, but yeah, for now, let this be. We'll see more later on. Any doubts on this? You should definitely try this on your own. So when you say potential at a point, you have to find due to all possible charges. And then we have something called earthing. So what is earthing? So when you take a conductor, it's connected to the earth. So earth is like a huge spherical shell. So It has a certain potential. It is actually a slightly negative potential. So any system that is connected to the Earth will have the potential of the Earth. Now, for convenience, we choose Earth ka potential to be 0. Technically, it is little negative. This is the symbol for earthing. So if someone shows you like this, a shell, and they show you the symbol for earthing, we can say the potential of the shell is 0. Quite a useful concept. So next class, when we catch up, right, we'll be doing a lot of problems based on earthing. We will connect shell and shell. We will see varieties. So charge is not conserved on a system which is earthed, because charge can flow to and fro from the earth. Charge is not conserved. Just give me a minute. Some people left. Let me take the attendance. There. So if you connect a system to the earth and if you put charge, there is no guarantee charge will remain constant. Clear with this? There. So make sure to go through the notes. We did almost 68 pages, and especially today's class, if you see, it was quite theoretical. And if you see, I didn't write any formulas, nothing. It's all statements only. So please make sure to go through this. Quite an important one. So next class, when we catch up, we will do some important problems. Those are also good. Shell inside a shell. If there are 2 to 3 shells, if you have plates and all that stuff. So next class, mostly we will wind up the chapter Gauss law. And then after that, we'll start off with capacitors. So Gauss law ka ending will be the beginning of capacitors. So both are kind of related. So next class is important. Okay, with that, we'll wrap up for the day. Right? We'll continue again on Thursday at 5:30 as usual. Remember, there's a test online. The deadline is Friday, 11 o'clock. So make sure to give. So Purvaja, bolo na.
Sir, I had a doubt on page 66.
So if you have any doubts, anything, you can stay back and ask, or else you're free to leave. So take care, stay safe.